in our simulation, we have already created stream number 1, this expansion valve, stream number 2, and chiller. So now we are going to add also stream number 3 has already been created. So we are going to add the compressor and the stream number 1. The compressor uses a horsepower to run. So here you usually have a shaft attached to an electrical motor or a turbine. So here our compressor need a horsepower. So we will have an energy stream over here too. And after that, stream number 4 will be entering the condenser. So back to our simulation, we need now to add a compressor. When we are adding a compressor, we need to make sure that stream number 3 has a vapor fraction equal to 1, which means all the composition is in the vapor phase. Okay, so this one, this will be 1, and I am going to close here. After that, we are entering this compressor. So this one, instead of K100, we are going to name this one compressor. We have an inlet stream of stream number 3, and the outlet will be, so here if we look in this message, you will find out you need a required a product stream, so it will be stream number 4. Also you need an energy stream, which will be our compressor horsepower. HP is for horsepower. So we have already added this stream, so now we are asked about the duty. So for the compressor connection, we need an inlet, outlet, and energy stream. And for the duty, it could be entered or it could be back calculated. So how it's calculated, we have a compressor with an inlet pressure, and we want to increase this pressure. So if we have an inlet pressure and outlet pressure, we can calculate the horsepower needed or the duty needed. So here, this is for the section for the connection. For the parameter here, we have the efficiency. It could be adiabatic or polytropic. This is really important to understand. If we have something adiabatic, it means there is no heat transferred, like as if this compressor is isolated, 100% isolated, and this is not an actual term. We have also the polytropic term and isothermal term. For the isothermal, okay, so let's describe this really fast. If we are talking about the compressor efficiency, we can express the efficiency in 3 terms. Isotherm for the compressor, and the second term will be adiabatic, which is available in an Aspen HYSYS, and third one is the polytropic efficiency. Okay, so for the isotherm means we are having a constant temperature, so there is no change in temperature. For the adiabatic, which means the Q is constant or the delta Q equal to 0, and here the delta T is equal to 0. There is no change in temperature. Here there is no change in the Q, so the system is 100% isolated. And for the polytropic, the Q is changing and also the temperature is changing. Okay, so this one, for the first one, this is impossible because the compressor increases the pressure, right? And when the pressure increases, the temperature will be directly increases. So the isothermal will not make any sense. For the adiabatic, it assumes that for some simulation consideration, we assume that the adiabatic efficiency at delta Q equal to 0. So it is not 0, but we are trying to reach the 0. So it's like we are trying to reach the 0. So this one, we are having it the efficiency adiabatic for the compressor to be fixed at 75% in Aspen HYSYS. So this is the default value. For the polytropic, this one is the changing, and this one is related to the real-time simulation, okay, or your real-time plant. So here both the Q and T is changing, and this information could be only given like this one. You can have this data given, and this one will be calculated from it. If we have 75 polytropic adiabatic, we can calculate the efficiency over here. So this is the first section for the design or for the parameter efficiency. So it could be adiabatic at constant or assuming there is no heat transfer, or it could be polytropic. And the polytropic could be calculated from these three references. Okay, here if we have information about the duty, we are asked here about the duty, so if we have any information we can write the value over here. The compressor can operate centrifugal, which means we are using the speed or the kinetic energy and converting this energy into pressure. Or it could be reciprocating, like we are opening our compressor, we take some amount, and we use like a piston to lower the volume and increase the pressure. So we have different operating mode. We usually stick with the centrifugal if we don't have other information. Or for the curve input operation, it could be single or multiple. This is coming from your compressor manual. So the pressure spec, you can define the delta B, like this compressor is increasing the pressure from 10 to 100, which means we have delta B, or increasing the pressure by 90. Also, you have the pressure ratio. This is an important term for the compressor. In pref, the PR, or the pressure ratio, or PR, is equal to the pressure at the outlet divided by the pressure in the inlet. So if I have a compressor, the compressor is decreasing the volume, so this one would be shorter, and we are attaching them together. So we have an in and we have an out. So if the inlet pressure is 10 psi and our outlet pressure is 100, this 100 psi, so we divide the outlet, so it will be 100 divided by 10, which is equal to 10. Usually we don't have this high pressure ratio, so this one is for the pressure ratio in the compressor, because if you are increasing the pressure this much from 10 to 100, you will have the temperature at the outlet really high, and the higher temperature can affect the material. Sometimes the material can be cracked because of higher temperature, and also it will need a specific design or material for the operation. So instead of having one compressor with a pressure ratio equal to 10, we can have 2 or 3 with a much lower pressure ratio. Okay, so that's why we have something called compressor station, or the compressor stage. So okay, let me elaborate more. So because we have for high pressure ratio needed, PR needed, we need to have multiple compressors. We don't use only one compressor. So the first compressor over here will be called stage number 1. The second compressor will be stage number 2. If this one with the inlet equal to 10 psi, we will have something between over here, and this one will be 100 psi. So we can calculate the pressure ratio, because the pressure ratio, if we have px here, the pressure ratio will be equal to px over 10 divided by 100 over px, right? So here you will have px square equal to 10,000. So the px, will be your value, the square root of 1,000. So that's how we calculate the px, and it's always recommended to have different stage, because now the temperature here will be moderate, and between the compressors here, because the temperature here will be increasing, we usually have in cooling system between the compressor. So you can have first stage compressor, and this has first stage cooler, and because we are increasing temperature, then it is fed to a second compressor, and after that we will have our second compressor or the second stage cooler to make sure the temperature will be maintained as a low temperature. Okay, so back to our simulation. If you have the pressure ratio, it will be written here. If you have the delta B, the difference in pressure across the compressor, it will be written here. The surge analysis, this is an important analysis, and it will be covered moving forward in this course. If you need to link this compressor, you can do the link over this section. For the rating, as I mentioned before, the rating is related more to the dynamic, but it's important to know that the curves could be added over here. Each compressor comes with like a manual, and the manual has the compressor curve. This compressor curve shows how this compressor can operate at different speeds. Okay, so this section will be covered moving forward too, but this is what we are looking for as a steady state. We have a vapor fraction, this is 100% vapor, and we have an inlet temperature. So this temperature, number 4, I'm sure it would be higher than 10 because this is a compressor and it is increasing the pressure and also the temperature. And here we have the vapor fraction. The properties will be calculated here, and this one for the composition, it's 100% propane, and PF will be left with the dynamic section. And for the performance, you can check the adiabatic or polytropic heat from here. Also, you can check the efficiency, like this one is already given, and the polytropic efficiency will be calculated here. If you need to know about the power of the compressor can be run by a motor or a turbine, and the compressor power will be displayed over here. Okay, and the torque will be over here. So here we are going back to our worksheet condition because we need to enter any other information that we have. So till now we are not given any more information about the exit pressure coming from this compressor. So now I am going to add our final component, which will be our cooler. Okay, so finally we have a cooler over here. Cooler. Okay, before adding the cooler, we have here an energy stream. If we double click to open this stream, this is an energy stream for the compressor horsepower. The heat flow will be displayed over here. This is the unit operation, the connection, it's connected to the compressor. Here we will have the information related to the dynamic and the structure. These two are related to the dynamic. So in our next video, we are going to add our cooler and close this cycle.